Hello and welcome to our presentation on designing actuation systems for animatronic figures via globally optimal discrete search. When we talk about animatronics, the first things that pops to mind are the lifelike animated characters from movies and theme parks. Here we see a collection of a few animatronic figures. We have Abraham Lincoln from Disneyland on the left, Karen from the movie Clash of Titans, and Captain from the movie Hitchhiker's Guide to the Galaxy, both in the middle, made by Biomimic Studios. And on the right we see Mesmer, made by Engineered Arts. Animatronic figures are electromechanical systems that are meticulously engineered to generate lifelike motions. These robotic characters can be made to convincingly resemble a vast array of creatures, real or imagined. Needless to say that the process of designing such models is extremely time-consuming and demands a great deal of experience. Let's look at two of these animatronics more closely. These latex faces appear very real and very complicated, but they are just a cover. Once you tear them away, you can see their true nature. Under the cover, we have a mechanism. An animatronic mechanism has two types of elements, followers and drivers. Drivers are essentially motors, which are attached by tie rods to followers. Followers make up the moving features of the animatronic. We also have force transmission elements. Those can be used to change the direction of force applied by the motor. Let's have a bit of a closer look, shall we? Given a mechanism that already allows all the followers to move in a desirable way, one of the big questions that still remains is how to attach drivers to followers. As I mentioned, drivers are connected to followers by tie rods. But the question is, which driver should be connected to which follower? Or in other words, how do we pair up drivers and followers in an optimal way? This is exactly the question we're set to answer. Let's start by clearly stating the problem. Our input is an articulated figure with a predefined range of motion for each follower as seen here in the animation. Additionally, we input a range of possible motor placements. The required output is an optimal assignment of motors to followers that enables the specified range of motion. We solve this problem by creating a tree where every leaf node consists of a possible final assignment. Due to the discrete nature of the problem, this leads to exponential growth, and already for a very little amount of motors and followers, we have unimaginable big numbers. To still find the optimal leaf node, we cast the problem into a shortest path finding problem, with the edge cost being relative to how good an assignment is. And now, let's see some results. First, let's start with a baby model with 10 degrees of freedom and 24 possible motor positions to choose from. The motors are stacked in two overlapping layers, each with 12 motors, to accommodate for multiple motors intersecting. We just don't create a child node in the tree if the parent and child node would intersect with each other. For this result, we created a shoulder mechanism with 4 degrees of freedom and 7 motors and 3 via points. First, again, we defined the trajectory, added some motors, and ran our algorithm. After, we can define any range of motion within the specified range of motions. And finally, the face. It has 14 degrees of freedom and 16 motors. We also created it physically. When we define the range of motion in simulation, we can directly translate it to the servos in the physical model. In conclusion, we built a tool that advances the traditional CAD software to simulate our animatronic designs. We use this simulation to create an algorithm that calculates optimal assignments of motors to followers. We also support via points, and please, if you want to know more about those, check the paper. We built a physical prototype to validate our design, and lastly, we added a bunch of simulated examples. Thanks a lot for watching.